Again, we are back with some more chemistry. As I said, I would talk about stable and unstable nuclei in this video. So we are going to start with that. Let's start with a stable nuclei. What the fuck is a stable nuclei? A stable, a stable nuclei is when uh, number of neutrons upon number of protons is approximately equal to 1. Okay, now an unstable nuclei will be either less or more than 1. Okay, in case of the tritium, we have two neutrons and one proton, so it's going to be 2, which is greater than 1. So it has an unstable nuclei. That's why it is radioactive. Next, we have effective molar mass. Effective molar mass. So for this, we have to learn another thing. Which is the different types of physical quantities. Okay, quantities. The different types of physical quantities. Tts. Okay. So physical quantities, right? There you go. We'll draw a line. I'll draw a line in the sand. Uh, famous Eminem line, which caused him a lot of backlash. But anyways, thumbsuck stick again. Intensive. There are two types of physical quantities that we have to talk about. First is extensive, next is intensive. Extensive is mass mass dependent. That is the correct spelling of mass dependent. And this is, of course, mass independent. Yes. These are additive and subtractive, while these are not additive and subtractive. We have multiple volume, mass, and other things. In here, we have temperature, pressure, density, extra, etc. So we know that extensive upon extensive is intensive. Okay, so mass upon volume gives you density, which is an intensive. So you can't just add densities. Yeah. So now we'll go to the EMM's formula, because effective molar mass is, what do you call it, an intensive quantity. So effective molar mass, EMM, is equal to mass upon okay, mass upon moles. All right, it is mass upon moles, mass per moles. So its unit will be, of course, mass per mole. I mean, what else do you want from me? And we know that total moles. This is for mixtures. For mixtures, this is for mixtures, because in mixtures we don't have this equal amount of things. All right. And now baby, let's say you have a container. This is an example. Let's say you have a container. You have hydrogen and you have nitrogen. You have 2 grams of hydrogen and you have 28 grams of nitrogen. So total moles are 2 moles Yeah, 2 moles. Then the effective molar mass will be mass, which is 28 plus 2, which will be 30, upon total moles 2, so 2 15. Now this is slightly towards um what do you call it, nitrogen, I think. Yeah, yeah. So it is more towards nitrogen. Yeah. Now let's say you have another example. You have 8 grams of hydrogen, goddamn, please focus up, and 22 grams of nitrogen. Yeah. So total number of moles will be approximately 4.8, and then you can calculate that 30 by 4.8 is 6.3. Yeah, and the unit is grams per mole, but sure, gram per mole. Yeah, so this is more towards the hydrogen side. Now note, if two gases A and B are present in ratio X is to Y, this is in, of course, moles, then the effective molar mass of mixture is U1. Let's say if this is the case, this is the case, and if it's Y is to X, then U2. Yeah, if it's Y is to X, then U2, and then U1 plus U2 will be equal to mass of A plus mass of B, where mass of A and mass of B are molar mass of gases. Yeah, got it? We can give you an example on this. Let's say if molar ratio is 1:2. Yeah, EMM is 40. Then find EMM of SO2 and O2. This is of that, okay, SO2 and O2 when ratio 2:1. So we know that U1 plus U2 equals to M of A plus M of B. U1 we have 40, so 40 plus U2 is equals to mass of A 64 plus mass of B 32. So this is U2 equals to 96 minus 40, which is 56. Yeah, grams. All right, cool. Next up we have calculation of moles, the main part of mole concept, that is. I'm trying to finish the chapter very quickly because I don't want to waste time, because at some point you will be just wasting time studying this chapter again and again and again and again. All right, those are my notes, by the way. I don't read off the notes, but I do have questions on the notes and for my revision. All right, so calc of moles. Calc of moles. So we have three terms in moles. We have mass, volume, and number of particles. Yeah. So for the first, number of moles equals to mass given upon molar mass. Simple, easy. For volume, we have multiple conditions, of course, but we'll just say number of moles equals to given volume per, of course, volume. Number of moles equals to number of particles for the particle 1, number of particles upon Na. Yeah. Next, so we can say now I'll give you some quantity if my device wants to focus. Can I turn on the flash? Yes, I can. Okay. All right. Now 1 mole, it can be divided into 3 subtypes. Molar mass at NTP is 22.4 liters, and we only have to study this to be honest, but at STP it is 22.7 liters, and Na, which is just 6.022 into 10 to the power 23. Goddamn. Now let me draw you a figure which will simplify basically everything. So this is moles. Now if you divide this by molar mass, you'll get mass. Now if you multiply this by molar mass, you will get moles. Alright. Now if you multiply moles by Na, you will get number of particles, and if you divide by Na, you get moles. Now if you multiply by 22.4, you will get volume, and if you divide by 22.4, you will get moles. Yeah. Now we know that PV, ideal gas equation, okay, ideal gas equation says that PV equals to nRT, where N is number of moles, R is constant, which does have a value, gas constant it is known as, T is temperature, P is pressure, and V is volume. Yeah. Now pressure has multiple units. Okay, so we know that P equals to F upon A, which is Newton per meter square, or this is known as pascals, SI unit of pressure. So 1 Newton per meter square is equals to 1 PA, Pascal. Okay. All right. Nice. Next, we have more. So 1 ATM, which is ATM, equals to 760 millimeters of Hg. Hg is of course mercury, and millimeters, or 76 centimeters of Hg. Now 1 millimeter of Hg is equal to 1 torr. I now 1 ATM is equals to 1.01325 bars. So 1 atm is also equal to 1.01325 pascals. Yeah, because then you can say that pascal equals to 1 pascal equals to 1 bar. Yeah, so these are all the units. Now units of volume, we'll discuss these units of volume. God damn. All right, technical difficulties. Yeah, I should just write on white plain paper. But anyways, units of volume. Yup, you're right. So volume is usually represented by L into B into H. Yeah. SI unit is meter cube. 1 meter cube is equal to 1000 liters. 1 centimeter cube equals to 1 ml. Yup. 1 decimeter cube, which is this 1 decimeter cube, which is just 10 centimeter cubed, is 1 liters. Yeah. Now temperature, we can express temperature in Celsius, Kelvin, or Fahrenheit. I don't know how to spell Fahrenheit, but I think this is it. 0 degree equals to 273.15 Kelvin. 1 Fahrenheit is equals to 9 by 5 degrees Celsius plus 32. So if 0 degrees Celsius, this will be 32 Fahrenheit. Yeah, cool. Alright. Now I won't teach you about standard temperature and pressure. Yeah. Do I need to teach you about standard temperature and pressure? I will not do so. Because I just do not want to be frank. God damn, what the hell? Why was that so fucking bright for 10 seconds? That just reset my fucking camera. Holy shit. R equals to, now R from the universal gas constant is equals to 8.314 joule per mole Kelvin. Yeah, if you want to, approximately 2 cal per mole Kelvin. Yeah, and 0.0821 atm Kelvin mole Kelvin, sorry, atm liter mole Kelvin, and 0.0831 bar liter mole per Kelvin. Now you can tell a lot by these units. Yeah, so if the temperature is in joules, you'll use this unit 8.314 because joules. Yeah, now if the thing is, goddamn, focus up, if the thing is in calories, if the pressure is in calories, you will use 2. If the pressure is in atm and volume is in liters, you'll use 0.0821. If pressure is in bars and volume is in liters, you will use 0.0831. Yeah, cool. Now approximate value of these, 1 by 12 and 1 by 12, if you want to use approximate values. Next up, and we have questions to do. But do you really need questions? No, you don't. You need concentration terms, yeah? You don't need questions because you can do questions by yourselves, right? I'm not supposed to tell you questions now, am I? I'm supposed to teach you theory. No, I'm not even supposed to teach you. I'm teaching myself. Not gonna lie. Not gonna lie. Yeah, solution is made up of solute and solvent. Yeah, this is more in amount and this is of course less in amount. Now concentration teams, concentration terms, yeah, concentration terms, yes, all right. Now concentration is defined as amount of solute upon amount of solution. Now we can calculate weight by weight percent, which is mass of solute, weight of solute upon weight of solution multiplied by 100. Yeah, we can calculate weight by volume percent. So weight of solute upon volume of solution into, this is in milliliters and this is in grams, into 100. Now volume by volume percent, yeah, volume of solute, volume of solution multiplied by 100. Now fourth is the gram per liter strength. You can understand by what it says. What does it mean? So this is just the weight of solute in grams upon weight of solution in liters. Now we can derive a relation between gram per liter strength and weight by volume percent. Yeah, we can derive a relation between that. Gram per liter is equals to weight per gram, weight into gram, volume in milliliters into 8,000. Why into 8,000? Because this will get divided by 1,000, just so we can make this into liters. Yeah, we'll divide this by 1,000 to make this into liters, so this 1,000 will come up. Yeah, now if you separate this from that, you'll get weight per volume percent into 10. Yeah, so gram per liter strength is equals to weight by volume percent into 10. Cool. Now let's talk about molarity. Yeah, molarity. So this is number of moles of solute dissolved in per liter of solution. Yeah. Molarity is represented by capital M. M is N by V in liters. So we can say that M is equals to N by V into milliliters, in milliliters into 1,000. We can also say that this is equal to weight of solute upon molar mass of solute, molar mass of solute into volume in milliliters into 1000. Yeah, yeah, okay. Now we can, do something with this. We'll do something with that. Don't worry. Don't worry, we'll do something with that. We're going to derive a relation between weight by volume percentage and molarity. So we can see that weight upon volume in milliliters into 100 is equals to 10 upon into 10 upon molar mass of solute. Now we can take this term and convert that into a weight by volume percentage, and this will be 10 upon molar mass. Yeah, or or we know that this is equal to gram per liter strength. So we can also say that gram per liter strength upon molar mass is molar mass is equals to molarity. Yeah, got that? Got that? Got that part? I hope so. You have got that part cleared up. Now give me 1 second. I'm rearranging some bullshit because I have to sit upright now. Alright. Why do I have to sit upright? I don't know. I just want to. So I will sit upright. So give me 1 second. I can put this on top of that. Yeah, alright. This is much better. Alright, next we have, and we can we can make a couple of cases from this. Yeah, give me 1 second. Let me think what I can do with this. I am genuinely thinking what I can do with this. Alright, let's say your density of H2O is equals to 1 gram per liter at room temperature. Yeah, so now find the molarity of the of H2O. How will you do that? How will we do that? Okay, now how many moles are we making here? We are making 1 by 18 for now, and this is per gram per milliliter. I'm sorry, gram per milliliter. Yeah, and this is 1 upon 1000, so we can just say 1000 upon 18, which is 55.55. Yeah, now I think I will skip over some of these topics because we don't need to study about these topics at this moment of time. We definitely do not need to study some of these topics at this moment of time. Definitely not study this moment of time. And now we can go back to our relations. Yeah, we can go back to our relations. So let's define a relation between molarity and weight by weight percentage. Now we know that weight into 1000 upon molarity into weight in milliliters, volume in milliliters. Yeah. Now we can divide and multiply that by m- the weight of solution. Yeah. Now we can separate some of this. Yeah. We can separate some of this. So we can separate weight into 100 upon weight of solution into 100 into weight of solution. This is a random. You don't need to memorize the derivation of this. Yeah. Molarity and V in milliliters. Yeah. Yeah. So this is equal to density, and this is just equal to bullshit. So this will be equal to weight by weight percentage into density into 10 upon molar mass. Yeah. Now weight of solution is going to be in kilograms, I mean grams, and per milliliter. Usually this density will be in grams. Yeah. Okay. Yeah. Okay. Next up, we have molality. One is molarity, next is molality. Mo molality, molestation. Yeah. Molality. This is just the mass of solute per kilogram, mass of solvent in kilogram in kg. Yeah. Mass of solvent in kg. We can also say this is mass of solute upon mass of solvent into 1000. This will be then in grams. Yeah. The unit of this is mole per kg. We can also write this formula as weight upon molar mass into 1000 into weight upon weight in grams. We can define this by a weight by weight percentage. We can derive a relation in that, but before we derive a relation in that, I think we should talk about relation between molarity and molality. Yeah. I think that would be a good thing to do. Yeah. I'm really sure that will be the best thing to do, to be honest with you. Okay. We still have a lot of things to do. Yeah, okay. No worries. We can cover this. Alright. Let's start with relation between molarity and molality. So M equals to, this is just a relation, just learn it, just take it in, don't worry about how it's derived. Molar weight upon 1000 into 1 by M. M is molality. Molality is represented by small m. Yeah. And this molarity. Okay. Now we can go back to n factors. Now I'm not gonna explain how n factors come because that is a very big topic. Actually, I'll do it because I am a good teacher. I'll explain to you most of the things except derivations because I don't want to do derivations. That's where I'm a bad teacher. Yeah. So we have acid, goddamn, acid, bases, salts, and redox reactions. We'll do this later. Yeah. First, acids. Acids is the n factor of acids is just the basicity of an acid, which is also known as number of H plus ions released by one formula unit of acid. Yeah, the n factor equals to basicity. Now I'll give you some acids and their basicities. I mean, yeah, their n factors. Acid, will make a table, and its n factor. So HCl has 1, H2SO4 has 2, HNO3 has 1, S3PO4 has 3, S3PO3 has 2, H3PO2 has 1, and H3PO3 also has 1. If I came down to starting to describe how the fuck this happened, it will take a long time, but I'll do it because I love you guys, and also I'll need a new copy because this has ended. I somehow finished this notebook in less than 10 minutes. I mean, an hour. Look at that. Yeah, so let's start explaining. So let's first talk about electron negativity. You've probably heard of this. If you haven't, there's a specific order. This will be the highest electronegative thing. So it goes phone call. It's a it's it's a thing that people use to just memorize this. Phone call, then bromine, iodine, sulfur, phosphorus, hydrogen, and boron. So as you can see, fluorine is the most electronegative and boron is the least electronegative. Now we'll talk about HCl. Let's start with HCl. So HCl has bonded like this. Yeah. So as we can see, Cl is more negative, electronegative than H. Yeah. So the electrons will be on this side. So they're sharing electrons, but they're on more on the side of chlorine. This is an ionic bond, of course, not a covalent bond. Covalent bonds are usually formed by carbons. Yeah. So this has a partial negative charge, and this has a partial positive charge. This creates a polarity, means one is more electronegative, one is less electronegative. So when you put this complex in this water, the HO, that's not how you make it, goddamn, HOO, this will be of course more electronegative because it is higher on the list, almost at the top. So it will drag the partial positive towards it, which makes it dissociate. So does HCl automatically loses its break its bond when it enters water? No, it is forced to break its bond when it enters the water. Yeah. This will happen if the hydration energy is more than the bond energy, greater than the bond energy. And this also means the compound is soluble. Yeah? Yeah. No. No, baby. Uh, H3PO3, yeah? H3PO3. Why does this only release two hydrogen? So let's make its first. Let's make its structure. Yeah. So double bond oxygen. You will learn how to make this structure. Let's just say you know this structure. Yeah. Let's just say you know this structure. As you can see, this has a partial negative, this will have a partial positive, this will have a partial negative, and this will have a partial positive. But these two will have basically the same amount of charge, as their electronegativity is basically very close. As you can see, phosphorus and then hydrogen. So this will not get out, but these two will get out. That's why their N factor is 2, because they released 2 hydrogen ions. Now in H3BO3, yes, I have finished this notebook. We have boron connected with oxygen and hydrogen, this connected with oxygen and hydrogen, and this connected with oxygen and hydrogen. But this still does not have a positive charge. This still does not release all three of its ions. Why is that? Well, because this is highly electron deficient. This is very high up in the list, but this is very low in the list, and this is very high in the list. As you can see, oxygen is very high and boron is basically at the end of electronegativity. So this will be very deficient. Yeah. Now when it combines with H2O, these will dissociate. The OH minus ion will attach to this. This will create a complex which is known as BOH4 minus. This will create that. Now this this ion gets attached to there, then this hydrogen ion is left. So plus hydrogen plus. So this is the N factor giving ion. So this does not release any of its ions. This ion released by the water is the H plus, is the N factor. See, pretty intense, I know. Now if you want to calculate pH, which is potence of hydrogen, it is minus log H plus. Yeah. Now I'll write down this reaction. H3BO3 plus H2O is equals to, gives BOH4 minus plus H plus. Yeah, cool. Now for bases, it's simple. It's really simple for bases. It's really simple. It's just the acidity of base, which is just the number of ions released. Yeah. Now number 3, salt. So it's just the N factor is just the total positive or negative. There's an or here, so it's either one. Yeah, look at NaCl, Na plus Cl minus, so plus 1. N factor will be 1. Now let's say you have a complex like like something like this: K2SO4 dot Al2SO4 whole thrice dot 24H2O. This is potassium aluminate. Yeah, this is potassium, not aluminate. I don't know. It's something like that. This has a n factor of 2 and this has an n factor of 6. You can calculate that. This is minus 3. Sorry, this is plus 3 and this is 2. So it's 6. Yeah. So then this will just add up because these are two salts combined with each other. So this will just add, which will be 8. And now I've run out of space. So give me 1 second. Do I have a notebook lying around here? I do indeed have a notebook lying around here. Goddamn. Goddamn. Yeah. Goddamn. That was a very far reach. Alright. What is this? Oh, this is my quantum mechanics notebook. God damn, I study a lot. God damn. Okay, so let's talk about normality now. Let's talk about normality. So what is normality? It is the number of gram equivalents of solute dissolved in per liter of solution. Got it? In per liter of solution. Now what the fuck is equivalent weight? Sorry, yeah. So let's write down the formula. Gram equivalence upon volume of solution in liters. Volume of solution in liters. Now what the hell is a gram equivalence? What is a gram equivalence? Very good question. It is weight upon n factor. Sorry, it is not weight upon n factor. It is weight upon equivalent weight. Yes. Yes. Now what the fuck is an equivalent weight? Good question. It is equal to molar mass upon n factor. There we go. That's why I made you study n factors. So we can write n equals to weight into 1000 upon E into V in ml, with where E is just equivalent weight. Yeah. Alright. That is the black body radiation, by the way. It's pretty interesting. I found it very interesting. That's why I decided to teach myself it. So we can also write that as weight into 1000 into n factor upon molar mass into volume in milliliter. This is equal to molarity. This is equal to molarity, yeah. This is equal to molarity. So we can say it just equal to molarity into n factor. Pretty simple, right? Pretty simple. Now you can calculate gram equivalence in many ways. So gram equivalence is equals to n into V. It's also equal to n factor into mass into volume. It is also equal to n factor into moles. It is also equal to gram n factor into weight upon molar mass, then it is also equal to weight upon molar mass upon n factor. This is also equal to weight upon equivalent weight. Pretty interesting, am I right? Pretty interesting. Now, let's start with mole fractions. Yes, yes. Very, very not interesting topic, but good enough, am I right? It is represented by an X type symbol. An X type symbol is written something like this. That is dot. It's chai, okay? It's kai. It's kai. It's kai, okay? I don't want to talk about it. I have a channel named Kai Reacts to Music. Go sub to that. I don't know. One more. B equals to 2 mole. And C equals to 3 mole. So B equals to number of moles of B upon number of total moles, which is 2 upon 5 in this case. It is the ratio of moles of total component to the total moles of solution or mixture. So mole fraction of solute is equals to mass of solute upon moles of solute upon n plus n, which is just number of moles of solvent. This is equals to number of moles of solvent. This whole thing is just equal to number of moles of solution. Same thing but opposite in solvent. Yeah, solvent. N upon n plus n. This is just moles of solvent and this is moles of solute. Yeah, so we can say that mole fraction of solute plus mole fraction of solvent is equals to 1. Why is that? We can just say n plus n upon n plus n. Yeah, you can clearly see that by the formulas. This is n plus n, n upon n plus n, and this is also capital N upon n plus n. So this will just be equal to 1. Yeah, cool. And what else? We can derive a relation between molality and mole fraction. It's just this, okay? Molality is equals to weight upon mass of molar mass into 1000 upon weight in grams. Yeah, we know that. Now this weight in is n, which is just moles. So it's n into 1000 upon weight in grams. Now we can multiply and divide this by molar weight. Yeah, you can multiply and divide this by molar weight of this solvent. So weight in grams upon molar weight into molar weight. Now this can just be written as this can just be written as n upon n. This is moles. This is moles of solvent, n upon n into n plus n, n plus n, which is just equal to 1 into 1000 into molar mass of solvent. Now this is just of solute upon solvent into 1000 upon molar mass of solvent. M equals to this. When are you ever going to use this? I don't know. But yeah, you're going to use this somewhere. Yeah, just remember this formula, okay? Let's say, for example, you have to calculate mole fraction of HNO3 in 0.1 molar aqueous HNO3 solution. Yeah? Yeah? Okay. So, sorry, 0.55. So you have been given 0.55 equals to chi of solute upon chi of solvent into 1000 of water. I'm sorry, of, I think, water. I don't know, bro. See, don't know. No. I don't know. Oh yeah, solvent. So solvent is just water. Solvent is just water. I'm tripping. Yeah, 55.55. So we have found this out. 55.55 divided by this is just 1 by 100. Yeah. And we know that chi of solute upon solvent, chi of solvent is equals to this. So chi of solvent is equals to 100 upon 100 into chi of solute. We know that this is just chi of solute minus 1. Am I right? Yeah. No. Minus chi of solute plus 1, which is equals to 1 equals to 101 chi of solute, which is 1 over 101. Okay. Sure. Yeah, sure. Am I right? Sure. Parts per million and parts per billion I'm not going to teach because it's not useful. That's why I'm not going to teach it, because it's not at all useful. You can learn it if you want to, but I'm not gonna teach it. If known and unknown are from the same, yeah, and we can go on to empirical formula now. But I really don't have much to teach an empirical formula, because I don't know what the fuck I'm supposed to teach in empirical formula. It's so fucking easy that I don't even know what to teach. But I'll still teach it because it's an important part of the chapter. Anyways. God damn. Yeah, alright. Empirical formula. Empirical formula. Okay, let's go more deep into this. Hey yo, what the fuck? I've been recording for 1 hour, man. I'm tired. It is the simplest. It literally says it in the name. The simplest whole number ratio, okay? It's the simplest whole number ratio. So, I'm gonna write this down. Whole number ratio. I. Now, let's say you have C6H12O6. 6 common. So, the simplest whole number ratio is CH2O. Yeah? Yeah. Now, we can do a question. We can do a question. Well, let me tell you the steps. So, let's say you have been given the percentage of carbon. So, you have to convert the percentage into grams. Just straight up turn it into grams, yeah? Don't care. Now, step 2 is to convert that grams into moles. So, weight into moles. Now, step 3, divide number of moles of each element by smallest value. Simple as that. It's as simple as that. It's not that tough, it's not that important either. But we can give you some, I can give you some formulas. Most teachers wouldn't give you some formulas, but I can give you some formulas because I'm the formula king, you know. If molecular mass is given, yeah, molecular mass is given. So usually if this does not come out to be a whole number ratio, you divide it by some, you multiply it by some number. So n equals to molecular mass upon empirical formula mass. Yeah. Then molecular formula equals to n into empirical formula. This is just to find out the correct, thing. You've found out the ratio, you'll calculate its mass, and yeah, that's it. Now, percentage composition. This is a good part of the story. Then we'll move on to stoichiometry or stoichiometry or whatever you wanna fucking call it, because it doesn't really matter. You just have to study it, okay? We are 1 hour 3 minutes deep into this, so I'ma just finish not the chapter, but like this lecture. So percentage composition. Mass of element into number of atoms upon molecular mass. So find out the percent composition of O in H2O. Yeah, it's 16 into 2 upon 34. What the fuck did I just write? I don't know. What the fuck? Huh? Huh? What the fuck? Oh, it's not 2, it's 1. What the hell am I what am I thinking? Advice is 34. What the fuck is this 34? It's supposed to be 18. 16 upon 18. God damn, what the hell am I? What is wrong with me? Multiplied by 100. God damn. My brain is not. What the hell is happening? Why is my brain not braining? Am I doing something wrong? Mass of element 16. Number of atoms is 1. Molecular mass. Yeah, okay. Yeah, this is the correct one. Alright. I don't know what have written that. Maybe it was H2O2 because then that would make sense. Yeah, it's probably just H2O2. I'm just tripping out, man. I've been studying for 1 hour straight by myself, teaching by myself. I'm talking to a camera, dog. I'm not talking to anybody else in the fucking room. I'm just talking to myself. Yeah? Stoichiometry now. God damn, I don't know how to teach stoichiometry, but we'll teach it anyways. Alright. Let's start with a simple reaction. Not a simple reaction. We're not even going to talk about a reaction. Let's just say, let me just tell you how to read a goddamn reaction. Because most people don't know how to read a goddamn reaction. Okay. So, let's say this is a reaction, yeah? This is a reaction. How would you read this reaction? Because if you learn how to read this reaction, half of the job is complete. Yeah? You read this reaction as A moles of A react with B moles of B to produce C moles of C and D moles of T. Small d moles of T. Okay? Got it? That's it. That is all. That is it. I don't know what else to teach you in this. This is basically it. What am I supposed to teach you in this? This is stoichiometry. Yeah, good. Now we can go to fucking reagents, man. Limiting reagents. I don't know, dog. I don't know, bro. What the fuck am I supposed to teach in stoichiometry, dog? Limiting reagent, yeah? Limiting reagent. Now, this is actually an important point. Okay? Limiting reagent. It is an agent which limits the reaction, yeah? What the fuck does that mean? Let's say, I'm going to come up with an original, very original reaction, yeah? A very original reaction. Yes, absolutely. A very original reaction. I don't know where to find this fucking reaction. Oh god. Alright. Let's say HNO3, yeah? HNO3 reacts with CaOH whole twice to form CaNO3 whole twice plus 2H2O. Now, to balance this, we'll put that there. Okay? Now, how do you find out the limiting reagent in this? We know that 2 moles of HNO3 react with 1 mole of calcium hydroxide to produce 1 mole of calcium nitrate and 2 moles of hydrogen oxide, which is also known as H2O or water. Now, simply to calculate the limiting reagent, there is a formula: moles upon stoichiometric coefficient. A stoichiometric coefficient is this, okay? Stoichiometric coefficient, and that's it. That's it. That's how you find the limiting reagent. Now, let's say you have 1 mole of HNO3, okay, and you have 1 mole of CaOH whole twice. This will consume up first because 2 moles are required for 1 mole of CaOH whole twice. So this will be the limiting reagent, yeah. So 1 moles are put. As 2 moles produce 1 mole of this, 1 mole will produce 0.5 moles. As 2 moles produce of HNO3 produce 2 moles of H2O, 1 mole will produce 1 mole of H2O, because this is the limiting reagent. So this will be where the reaction basically manipulates or gets used. when all of this is used, a certain amount of this will be formed and a certain amount of this will be left. How to calculate what's left? 2 moles of HNO3 reacts with 1 moles. Now if you have 1 mole of this and 1 mole of this, there will be left 0.5 moles, because 2 moles react with 1 mole, so 1 mole should react with 0.5 moles, but you have 1 mole here, so you will have 0.5 mole left over. Yeah, makes sense? Makes sense. Now I can teach you another application of stoichiometry. Yeah, I can teach you another application of stoichiometry. After that we'll end this, because this is gotten too long and I want to enjoy my day too. You know, I have my life too. We know that these are stoichiometric coefficients. Yeah, let's say there are B moles of this, Q, sorry, this will be confusing, L moles of this, Q moles of this, R moles of this, and S moles of this. So L upon A is equal to Q upon B is equal to C, sorry, R upon C, and that is equal to S upon D. Yeah, what does this mean? This does not mean anything. It's just a equation which is always true for every single reaction. That's it. This is true for every single reaction, so you can find out however many moles are of that substance. Yeah, that is basically the use of this, because you know, A is the stoichiometric coefficient and this is the number of moles. Yeah, so number of moles upon stoichiometric coefficient will be equals to this number of moles upon stoichiometric coefficient. So you can always find the number of moles that needs to be reacted with something else. Yeah, this is a basically this is just, you know, balancing the equation, but in you can find out the actual amount that is required for a reaction and how much amount will be actually produced, and which I've told you how to figure out the limiting reagent already. So that is it, I think, for this lecture. A very lengthy lecture, I know, but a very informative lecture, and most of your chapter is now covered. We have finished the concentration terms and basically everything. We are on stoichiometric coefficient and we have done limiting reagent. Now we have redox reactions left over and a little bit of stoichiometry left over, which we will cover in the next lecture. Will be after like 2-3 days. Okay, I'll meet you then. Goodbye. Thank you for watching. My exams are going on, so lectures will be less frequent because I have to study for exams myself. Yeah, okay. Thank you for watching. Goodbye.